Hi, Dennis Barber on the line.
Hey, Dennis, it's Lewis. How you doing?
I'm doing well. How was your 4th of July?
Oh, it was okay. How was yours?
Uneventful, which is always good. It was just a nice, quiet,
Yeah,
day. Are you
same
able
here.
to log on to see the screen?
Yeah, so what I had to do is I had to forward the meeting info to my WS Nelson email because I clicked on the Exxon email link and basically said like, you have to download, go to meeting, and they have their rules and everything. So I got it on my my Nelson screen here, so I can see it. Regarding the other guys in the field, we'll see if they can jump in. The guy Ian knows about it. I spoke with him this week, so I'm hoping he can call in, or at least call in on the
So that's
audio
fine.
if he can't get the video.
I understood. I'm recording it as well, and I'll also send you the slide deck when we're done. I wanted to send it to you in advance, and it's been. I'll never complain about being busy, but we have been just extremely. We have been jammed up on. Yeah, we're actually even on technician bandwidth. I mean, I'm actually getting out to the field now myself to help get some of these projects along. So again, not complaining. Just it's been good, but it's been very, 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 very busy. So that's and it's put me behind on some of my other things. So like I said, when we are done, I'll send you the link to the recorded presentation as well as the just the bare bones PowerPoint as well.
Okay, that's good. Yeah, like I said, I asked him, I said, just in case you have trouble, what kind of questions did you want to ask? And he really just said what do you call it, knowing when to equalize and can they equalize, because there's little stickers on all of our chargers that say, do not put an equalize. Or do not equalize.
And I'm going to go over, like I said, I give a very brief overview of the different battery technologies, knowing that from what I understand, 99% of your batteries are valve regulated lead acid, and they only require equalization under direction of either the manufacturer or a certified, the service companies such as ourselves. The problem is some of those equalization circuits, they have timers on them. Timers don't always work properly. Sometimes they're manually put into equalization with the idea that you have to take it back out. You have to knowingly take it back out. Flooded batteries and NiCad batteries, some of those other flooded technologies are more resilient to withstanding high charge rates in case someone forgets or timer fails. Valve regulated, it's a death sentence. So that's why they're like, hey,
that's probably why they have the notes in there.
Yep, and they really don't require it. Like I said, it's really very infrequently that equalization is called for on those batteries. So that's why, that's why the stickers have to do with the battery technology that's being deployed. The other thing, pardon me, with the equalization, I was going to actually take a step back. It's very infrequently even really needed for the lead calcium flooded batteries of today. That was more back to the days of antimony and some of the very early chemistries that were used that did require periodic equalization. So honestly, it's almost something they should really take out a lot of the chargers at all.
And its main purpose is to get all of the cells back to the same voltage. Whether or not they're all the same already. But
yeah, no, that was usually one of the indications. If you had a spread of individual cell voltages, some running high, some running low, and I'll be honest, once you hit it with the equalize, it did flatten it out, but they would spread usually fairly quickly after. It was a short-term remediation. Yeah. Right now, the equalization, as I see it being utilized, is really if you want to get your battery you came off a deep discharge or batteries are stored for an extended period of time, it can help drive sulfates off the positive plates. Any kind of sulfation or crystallization that you may have, it can help in that end. But and it obviously also speed up, the amp battery back in quicker. But again, even there, you really don't even want to do it that because of the heat and everything like that comes with pumping a lot of current back into a discharge battery. If you can, you really kind of want to meter it in slower. So, but yeah, the equalization was really pretty much to try to like you say, get all the individual cell voltages in line.
Right.
And honestly, at the end of the day, a spread of individual cell voltages, people used to get really uptight about it. It's from having performed load tests on thousands of cells, I can tell you when you go in, flow voltage has no indication of, or very, very limited indication of the health of the battery, whether it's floating a little bit high or a little bit low, even outside the recommended window. Very little correlation to actual how that battery or how that individual cell can perform under load or even the life of it.
Right, not as much as the impedance, right?
Impedance, I tell you what, if I could tell any technician what they should really have with them when they go out to do a PM, an impedance meter, an amp clamp, and a temperature probe. And those three things will tell you much more about the health of a battery than really anything else. So
interesting. Okay.
Yeah, we'll give them a minute here. And like I said, we're recording now, so the audio should be being captured as well. So it's not too onerous. I believe it came out to like 45 slides, and like I said, I'll put out a summary and we can.
No, yeah, I mean, I really appreciate it. I know y'all are busy.
No. I wasn't. No, what I was saying about that, actually, it's today's a pretty good day. Our office is closed for all intents and purposes. Pardon me, which I was.
Yeah, same here. Not a lot of people here.
I called in and they're like, "Oh, no, today's." I'm like, "What?" I didn't even realize that. I tell you what, I'll start stepping through it, and if someone is able to join or comes in, that's great. We can back up, or like I said, let's see if I can get this.
No, that's good. And I sent the chat to the guy, so it looks like he's away from his screen. So
okay.
If he went to call in, I told him to call in to the audio just in case he wants to do that too. But okay, yeah, this is good.
Okay, well, the way I always start, the terms they're pretty fluid depending on who you're talking to. Yeah. They'll interchange terms for the purpose of this presentation. A jar and cell is the most basic part of the battery. 2 volt in lead acid. When you get into NiCads, they're 1.5 volts. Their chemistry is different, but everything that I know that you have deployed is either going to be valve regulated or flooded lead acid. So that's going to be 2 volt, and that's nominal. So anytime someone talks about a 120 volt system, they're typically talking 60 cells. Even though that system in service will be floated at around 135 volts to keep everything properly charged. Again, it's just a monoblock. Similar to, I'll say, a car battery is what most people can relate to. They see them deployed in the field. And I did see actually some in your network as well. They come in 4, 6, 8, 12 volt. More often than not, they're 6 or 12 volt. Strings, that's when the assembled cells or monoblocks are put together. Again, they typically, when you get into communications, emergency lighting, things of that nature, they're usually around 12 or 24 cell systems, 24 volt, 48 volt. And then your gear and UPS systems typically run 120 to 240. Now there are 480, 180. These are just kind of the more standard voltages that you'll see deployed. Battery. That battery can be the cell, the monoblock, the string, depending who you're talking to. That's still throw that term around. Flooded and vented. We're going to talk about the two different technologies. From what I saw of your assets, primarily you are the sealed valve regulated lead acid, and sealed is a misnomer. They are not sealed. They do have pressure release valves on them, but again, it was a marketing thing that was done years ago. That same thing with that maintenance-free moniker that was helped to push to push that technology when it was relatively new. And then gel. A lot of people think gel and AGM or valve regulated are necessarily the same thing. Gel actually uses silica to immobilize the electrolyte. So you don't have in an AGM, a Zorb glass mat, or valve regulated battery, you don't have acids sloshing around. The theory is that you can turn the battery on the side, which is how most of them are actually installed, and you won't have electrolyte or acid running out of the battery. So it's immobilized in a Zorb glass mat technology through the separator, and then in a gel they actually use a silica base to solidify the electrolyte or give it a partial fluid state. The gel are really, I tell you where I see 90% of those deployed are outside plants, cable companies. A lot of times if you see cable boxes, sometimes on the side of poles, pardon me, for either signal boosting, stuff of that nature, that's usually where you see gel. So you don't really see a lot of gel in your application. Ampere hour, it's really the size, the capacity of the battery, and that's really dependent on surface area of the positive plate. So typically, physically larger the battery, the larger that stored energy capacity of the cell is. So in the U.S., we usually define ampere hour at an 8-hour rate. So when someone says a battery is an 800 ampere hour battery, it can provide 100 amps constant current for 8 hours to a end voltage of usually 1.75 volts per cell. It's kind of important when you look at European batteries. They use a shorter, it's not apples to apples. They use usually a 5-hour rate. So that's really more of a sizing issue, not so much a maintenance issue. But that's something to keep in mind as we're talking. Yeah, as we're talking. Plate separators and posts, we'll look at those. Electrolyte, acid, specific gravity. You don't really have the luxury of checking the strength of the electrolyte. It's sulfuric acid-based electrolyte. Higher the gravity, usually that kind of juices the cell. It's higher performance. You'll get in a specific gravity of 1.215 and 1.30 are kind of standard in lead acid batteries. At the 1.215, same battery, less performance. At 1.30, higher performance. The thing with the higher gravity, though, you accelerate your corrosion rate. So there's a trade-off. You get better performance, but you kind of have to design around a shorter service life. So what they do is they make usually thicker grids, things of that nature, to compensate for getting that beefed up ampere hour or beefed up power density. Float versus equalize, we touched on that, so that's important. Float is just the battery. I didn't include open circuit. That's when a battery's just in storage or offline. Design life versus service life is actually pretty interesting. The design life of a battery is, if that battery dies of natural causes, grid corrosion, things that just happen in the normal life of a battery in service, they design around that. So they'll design grid thickness, amount of electrolyte, the paste. It's all designed with the idea that, hey, this battery is typically valve-regulated batteries are either a 10-year design life or a 20-year design life. 10-year design life is usually that monoblock car-style battery. So that's what it's designed, if it would, in a perfect world, how long it should last. The 2 volts, the Absolites, the East Penn product, the Unity product, stuff like that, that's in your, out in the field for you, is a 20-year design life. Service life is a different thing. Hey, what are these batteries really performing? Those monoblocks typically, depending on environment, cycle, a lot of other variables, but typically those batteries are lasting about 5 years. And the 2-volt valve regulated, I think your people will probably agree, they're lasting 7 years, 9 years, 10 years. Certainly not the 20 that they, market as part of their design life. Discharge testing, capacity testing, acceptance testing, those are all different terms that as put out by IEEE. Typically, we just call it load testing. And that's really the best way to determine the health of the battery. And I don't have it on this terminology, but ohmic testing with a Medtronics tester or a Megger, that's the second best way, I'll say, to probably determine, your actual capacity. But a load test where you bring in a resistive load bank, take that battery offline, run it down in a controlled way to determine end voltage at a published discharge rate is really the only way you can, determine your actual health of the battery. And then charger, rectifier.
Capacity test?
Capacity test, correct. Yeah, capacity test, load test, acceptance test. Acceptance test obviously is kind of done at installation to make sure what they sold you was actually delivered and installed as far as performance. But yeah, you can interchange all those definite terms, pretty much. But yeah, the capacity test and load test, discharge tests are all the same thing. And then rectifier or charger, the DC plant. The standards that most people work under are the IEEE. Utilities also have some other standards, North American Electric Reliability Council, the NERC, and there's a federal NERC and FERC, as it's referred to, comes into power generation. But for most telecommunication, UPS, and switchgear utility and chemical, petrochemical applications, IEEE is the standard by which most people write their routines around. Their maintenance is usually written around their specifications or their recommendations. So 1188 handles the valve regulated, which is what you are primarily using, 450 for the flooded or vented batteries, and 1106 for the NiCad. I did not see any nickel cadmium in your, at least in the inventory of the Hoover.
Not on Hoover, no. They have probably some that I'm not sure of in Mobile, but yeah, these look like all valve regulated, and then a couple of just car batteries, I think. So. Okay,
right. Right. Honestly, we do actually see quite a bit of NiCad use in your industry as well. It looks like you guys have more or less gotten away from them. And there's additional IEEE documents for installation sizing related to both the flooded and valve regulated batteries. And not to forget, there's a bunch of other NEC building code. So there's a lot of considerations. This, again, not so much from a maintenance perspective. This is usually design and installation. Things that need to be.
I didn't even know about this.
Yeah, there's a lot of consideration when looking at a battery, and not only the battery but also the auxiliary. Some of seismic requirements for the racking or installation itself, how it gets anchored, spill containment, what's required there. Yeah, so there's a lot of considerations that need to be taken into when looking at the initial design or install. So this is a vented or flooded battery. This particular one is a 4-cell jar, so it's 8-volt, nominal 8-volt. But the idea here is a lot of these same components, strapping jar, positive plate, that's common to all battery designs. What's I'll say an advantage to this particular design is it's a jar you can see through. So you can look at sediment buildup at the bottom. You can look at plates for crystallization or sulfation. You can look for corrosion inside the battery separator falling apart. And then it also has additional ability to sample the electrolyte, so you can look at the state of charge of the battery. You can also, along with this battery, you have to periodically add water to the electrolyte. As these batteries are in operation, they off-gas hydrogen and oxygen, so there's consideration that has to be made for ventilation. And again, they have their own, these jars are somewhat, I'll say, fragile during installation. They're usually a PVC or a polycarbonate material that, they can break. So you have to be careful when handling it, working around any battery, but these in particular, and primarily on installation and de-installation. You have a lot of the same components in the valve regulated, cover, negative plate, positive plate. Now, this is what I was talking about. This white material is a glass mat separator. So it's a spun porous material that actually has the acid absorbed into it. So the separator not only keeps the positive and negative plates from shorting against each other, it also retains the electrolyte. Now, keep in mind, these plates are also a grid design. They're pasted plates, and the paste material is usually a lead, calcium alloy compound, and it's very porous. So the acid or electrolytes actually also absorbed into the plates as well. So you're looking at a light gray negative plate, and the positive plates are the darker lead oxide material. But again, opaque jars, you can't see into them. Instead of a flash arrestor where you would add water or a sample electrolyte into it's a pressure relief valve. That valve itself is fixed into the jar, and it's not meant for periodic removal for anything. That's where the term kind of sealed comes into place. And these valves typically release around 3 to 5 psi depending on the manufacturer. So if these batteries see high temperature, high heat, anything that would cause the positive pressure inside so the cell itself won't rupture or blow apart, there's a valve that'll reseat after pressure release. So there's the straps. Again, this is where you can actually see quite a bit of potential issues with the battery, corrosion, and things of that nature happen here. But again, typically you can't see it. And I'll show you how we do actually as part of our preventive maintenance do look at those straps, but I'll show you some of that a little bit later. And then this is the monoblock. I'm missing the arrow. But the pressure relief valves are actually usually seated under the cover. Sometimes you'll see them, sometimes you won't. This is a 12-volt battery, so it's 6 cells in series, usually with a positive and negative terminal, 12 volt. Again, positive and negative plates, separators, very similar material to the previous battery, just kind of assembled into a smaller monoblock. So vented, flooded batteries, even there you have different technologies, different flow voltages, different maintenance routines, antimony, selenium, calcium, or some of those. The valve regulated, for the most part, they're pretty standard. They do have some batteries with cadmium in them. That's the Absolite, older Absolite series batteries from GMB. So consideration needs to be thought about when recycling. Not a lot of smelters will take batteries with cadmium in them. There are some new technologies being used in the negatives, the nanocarbon technology now in valve regulated batteries, improving their ability to operate in hot environments, high temperature environments, and also improving cycling capability. And there is a low gravity available. The reason that the low gravity valve regulated battery was developed was so that it could be installed in parallel with vented lead acid batteries. Vented lead acid batteries typically float around 2.21, 2.22 volts per cell. Standard valve regulated batteries float around 2.25. So they made a low gravity version to float around 2.21. So they could be paralleled with lead acid. And then again, NiCads, even within that technology, there's different process. Pocket plate, plastic bonded electrofiber. Those are really just manufacturing differences in the technologies. They pretty much perform, and the maintenance is very similar to them. But again, something to be considered when designing or engineering a plant. But so I threw in some pictures so they would recognize, hey, this is what your people are used to seeing out in the field. These batteries are typically installed horizontally. That's the idea. It gets you higher floor loading, but it gets you power density because you can stack these guys up pretty tall, as opposed to along a battery rack. And again, it's just power density and footprint is much more advantageous. This here lower corner is a picture of actually just a cell. So the cell has been unloaded from the steel tray. And it's actually interesting. I have a picture later in the presentation of the back of one of these. So just keep in mind what this thing looks like, and I'll reference that battery a little bit later. So why ExxonMobil is using valve-regulated battery? Again, the density, the self-contained rack tray, so that there's not another component that has to be assembled. They're usually shipped in their final assembled rack, as it were, in the steel casings or steel cans. Limited off-gassing. You don't need special ventilation. Typically, you don't need hydrogen detection incorporated with a valve-regulated battery install. You do not regularly add water to the battery. As a matter of fact, it's very difficult to do that. And robust design, the hard plastic robust, again, you can drop one of those batteries and you're not going to have free electrolyte spill all over the room. There are some drawbacks to this design, this technology. It's difficult for inspection, and that's where that internal ohmic test meter comes into play. If you really look at the IEEE maintenance recommendations on the battery, it's actually more onerous on these batteries because they do have a shorter service life. So you really have to stay on top of them to get ahead of the curve and get a predictive end of life on these batteries, as opposed to a flooded battery where they really do kind of, their life, as their capacity goes out, it's a pretty flat curve. You get out to a NEA curve around 80% of capacity, it starts to drop off quickly, but that's usually around 18 years of service. These valve-regulated batteries, it's a much more linear loss of capacity, and like I said, some of the failure modes can be rather quickly lead to a rather quick loss of capacity. So you really have to stay on top of these batteries for maintenance, so you're not unexpectedly surprised by a dead battery. Shorter service and cycles. They are less tolerant to heat because they are in steel cans and they're typically stacked on top of each other. Their ability for convection cooling is not as good as it is in a flooded battery. Flooded battery, you have that free floating, electrolyte. They're open rack design. They're open, so they're much more tolerant to heat. They can dissipate heat a lot easier. And then I mentioned before the rapid potential for rapid capacity loss is important, to when thinking about this. So a mobilized electrolyte, no water addition. The idea about the valve-regulated battery, and you'll hear the term recombination. And I didn't get into the electrochemistry of this, but I do have a whole presentation I can send you on the side for the electrochemistry that goes involved as far as the battery under charge and discharge. Yeah, and then there's Tafel curves, and there's if you're into that, typically this is kind of designed around maintenance, but I can send you ad nauseum some stuff on the exact chemistry. But at the very basic level, what happens is the electrolyte is broken down. Hydrogen and oxygen are actually end result of the charge process. They're broken down on the positive. The hydrogen and oxygen recombine because we have that pressure relief valve on it. It's forced to recombine, and it recombines on the negative. Now that's good. The idea, hey, we're limiting water loss. We don't have to add water to the batteries. Yeah, well, another thing that wasn't really accounted for in the original engineering of these batteries is that hydrogen and oxygen recombining on the negative actually depolarizes the negative. It undercharges the negative. So that's another issue that comes into play with this shorter design life, or design life versus service life. It helps shorten the life of the battery. But it is a closed loop process. And again, the idea is, hey, these things you don't have to periodically add water to, and you don't have hydrogen and oxygen just freely venting out of the cell into the room. There is positive internal pressure. I mentioned before, usually about 3 to 5 psi. Gassing is managed by the valve, and compression is also an important part of the design of this battery. As I had that slide before, or one of the previous slides, I had shown the absorbed glass mat not only keeping the cells from shorting out as a separator function, but it does have the electrolyte in it, and it's important to have physical contact between that glass mat and those plates, so the electrolyte, the electrochemical reaction, can has a path. So, and honestly, and that's a lot what those testers or meters are looking at. I'll use Medtronics just because I believe that's a tester that you utilize. But that's what it's looking for. It's really looking for the conductivity between the most positive and negative terminals of that battery within that battery. So you're looking to see it. Hey, that battery is drying out. You're losing compression. You're getting sulfation on the plate. Any of those things that are going to impede the ability of that battery to, perform what it's designed to do, that's picking up the resistance. So again, conductance is just the inverse of resistance, but that's what that test set is looking at, a bunch of different variables that can limit.
I do know now at Hoover they're just using the Byte 3 tester. And,
okay, are they using the Byte? Okay, and that's fine. That's again, that's yeah. So you had the Byte, you had the Byte, you had the Medtronics. I thought that maybe they were using the Medtronics, but you had the Byte, you had the Medtronics, Megger, and there's 2 or 3 other manufacturers out there, but they're all pretty. From our standpoint, we use the Medtronics only for just ease of use, but in our experience, the Byte is actually a little more cumbersome to use, but the results are the same. The readings that you're getting with that test set are as reliable as any other test set out there, I guess is what I'll say. So
it's a little more bulky, right?
Yeah, it's a little more bulky. Yeah, it's a little slower to use. But it's whatever and we have 3 different test sets. Sometimes it's depending what customer dependent. They'll say, hey, we already been trending with this test set for a while, and we're comfortable with it. So fine, we'll use that, and that's what we'll keep. The important thing to do with those test sets, they don't so much have a pass-fail number to them as they do a trending ability, and that's really what you're looking at. There are nominal values that are provided by the manufacturers for those batteries, but what any of them will tell you is, listen, every battery is in and to itself is unique. So, and even depending upon the charging equipment that's being used, the environment, they say once you get that battery installed, get a baseline and then use that as a reference for. Now, you don't have that luxury. Sometimes, we'll come in a couple of years after it's been installed. We don't have a history on it. And then we will use the manufacturer reference value. But what you really want to do is establish a baseline and look for deviation from that. So as that battery ages with that Byte, that resistance is going to go up. I have it later in the in my slide, but usually we use a 20% delta from that baseline as a warning and then a 30% as, I'll say, like an alarm status. And even then, those test sets are useful, but then we usually use that 20-30% threshold. We want to, there's a couple other things you'll look at: age of the battery, the cycle, the application, all these other things. And if it seems like, hey, this is kind of where we would expect to the end of life of the battery, then we'll say, hey, start budgeting for replacement. If it's an individual cell that's dropping off much quicker than the rest of them for whatever reason, then we'll replace that individual cell. And if the overall battery, it seems to be dropping off quicker than what we would expect to see, then we'll recommend a load test. We'll say, hey, this thing is trending not what we expect to see. Let's get a better picture of what's going on with the battery, and then we'll go ahead and recommend a capacity test or a load test. So failure modes, what happens? Sulfation can happen on the positives. There's a couple items that can happen on that. Consistent undercharging. It's not uncommon for us to come across a battery. We'll see a manufacture date of, say, 2017, but an installation date of 2019, like it was just installed this past year, and the battery was stored for a year and a half, and which is in and of itself is not necessarily bad as long as they periodically charge that battery while in storage. So there's something that's, like I said, that's more common than what we find, but we do occasionally find faulty rectifiers or chargers that are set wrong or actually failed or lost their ability for regulation and then undercharge a battery. There's not a lot you can do for that. That is where equalization could be utilized to help kind of drive those sulfates off the plates. But like I said, for the most part, if left too long, it's permanent damage. It's very hard to recover from a battery that's been, say, a battery that's been stored for 3-4 years, whatever, without being charged. They're usually not recoverable. Overcharging or high temperature. The grid corrosion is, I had mentioned before, that's kind of the process of a battery just as it's in service. We do try to, try not to overcharge. This is why we say about the equalization can be dangerous with people just forgetting that it's in the equalization. Again, once you accelerate grid corrosion, there's no return, there's no fix for that other than replacement of the battery. So that's permanent damage. Overcharging or a battery in a high temperature, all the manufacturers have a sliding scale. So if some rectifiers have temperature compensation circuitry already incorporated into them, so that, your battery is going to be operating at 90 degrees F for certain parts of the summer, but yet is susceptible to lower temperatures in the winter. There's circuitry that'll actually lower that float voltage in the summer and then raise it in the winter. So that can also manually be done. Again, that's for the most part, pardon me, they usually set it and forget it. So that's why it's for a technician or someone to manually do that. They really have to be, the batteries have to be on some kind of quarterly routine or something that they're constantly looking at that, so they can tweak it back and forth as needed. And certainly try to use a temperature controlled environment whenever possible. Now, the other thing with a high temperature or a high charge current on the battery, you can also, you're going to dry out that battery. You mentioned that that one-way pressure relief valve will off gas when pressure is built up due to high temperature or high charge current. Once that gas is gone, there's a process to put it back in, but for most service people, they don't do that, and they're honestly are not encouraged to do that. So once that gas is gone, you start to lose surface area contact of the glass mat and the plate. Anyway, so the battery is going to start to actually try to draw more current to charge the plate, and it's going to create more heat, and it's going to drive off more gas, and it's called call for it's called thermal runaway, and it's a condition once the battery starts. I'd mentioned before an amp clamp being a very important tool in your arsenal for maintenance or predictive maintenance of these batteries. You start to see an increase in flow current. Usually it's in the magnitude of milliamps per 100 ampere hour. So 1,000 ampere hour battery is going to draw an amp of flow current. You go into a battery room, or you go into a battery and you clamp that battery and it's fully charged and you see 5, 6 amps. You know you're on your way to some kind of, some kind of problem. We've been deployed. As a matter of fact, we just came off a thermal runaway situation up in at a utility in in New York. The battery was 170 degrees Fahrenheit, drawing 25 amps, and it was a 600 ampere hour battery. So, and it doesn't happen overnight, but once there's always indications of it, and it's a slow kind of creep, but then it just takes off. So, this is a battery that wasn't looked at for months. It did happen within a year period, but somebody under quarterly or even semi-annually maintenance would have picked up on that issue before. Like I said, at that point it was someone had picked up it'll smell like sulfur or rotten eggs. There's a pungent, and then physical heat off the battery. So it's, like I said, by the time you get to that point, it's again that's beyond repair. Then once you reach that point, so avoid overcharging, monitor ambient temperature and battery temperature. So usually we look for a difference between those two. Flow current, limit equalization intervals if you do have to equalize it all. And there is a catalyst option available for valve regulated batteries. I mentioned before the hydrogen and oxygen that are coming off the positive plate being recombined on the negative. And I'll touch base on this again a little bit later in this slideshow, but there's a catalyst that some manufacturers supply and others they can be retrofitted into. The material is palladium, and it's affixed to that pressure release valve. And instead of the hydrogen and oxygen recombining on the negative and then underpolarizing or undercharging the negative, the hydrogen and oxygen recombine in the headspace of the cell, and they actually re-wet from the top of the cell, and then that wicks through the battery, and that will help extend the life of these batteries. Again, I'll touch on that a little bit later, but that's another option. This is what I was talking about, just a crude representation of compression. But as the compression or the battery does start to dry out, if you imagine you're losing surface area, contact area. Here, so you're taking, say, a 100 ampere hour battery on the left. Now you've cut in half your surface contact area on the right. You've now taken a 100 ampere hour battery, and now you have a 50 ampere hour battery. So that's where we come into the idea of, hey, capacity loss. So again, it's kind of crude, but it gives you an idea. Thermal runaway, this is as flow current increases, the water loss increases, and your capacity drops off. Again, you're just exacerbating the dry out of the battery. I hate to say this isn't really a failure mode, but poor loose connections are also important to monitor on the battery. I will say, I don't believe I've ever seen a battery connection loosen itself out in the field. It's usually, if we've seen poor or loose connections, it's from time of install, and no one ever just caught it. It was a misconnection at the time that it wasn't torqued down, and it just wasn't done. Now, connections can go bad if corrosion's allowed, if there's a post seal failure, and corrosion starts to form around the post and gets in between the surface mating area of the connector and the post. But for the most part, like I said, the bad connections we see are usually from the install. So we do recommend using a digital low resistance ohm meter and checking the resistance of that strap, and then doing visuals for corrosion. This particular battery was a UPS application, so a very high rate under discharge. None of these connections were torqued. So whatever installation group did the battery, it went under, say 700 amp load, 800 amp load. Is designed for like a 15-minute rate. it actually this portion of the battery melted down and caused fire, but all throughout the battery, all these connections had heated up and actually started to melt the post. So again, typically once you take care of it from the initial install, you're okay, but that's, like I said, something to keep in mind. So good practice. I'm not going to read through all of the slides, but the connection resistances can vary depending on the length, the span of the connection resistance. Usually they're uniform within the string, but occasionally you'll have a cable or something that'll jump stack to stack. Obviously those will be higher. You go back to the manufacturer, they'll give you the recommendation on what those resistance readings should be. PPE, sure you have your own standards as to what technicians are required to wear when they're out servicing the batteries. The total DC voltage is going to also drive that. So you could have a nominal, emergency lighting battery that's 24 volts, or you could have a 480 volt, UPS or 120 volt switchgear battery that's going to require a different level of protection. This is our minimum recommendations. Safety glasses and or a shield are paramount, as well as gloves. And then again, hard hats, the hearing, that's all going to be environment driven. Absolutely recommend factory insulated tools. We don't, and we've seen it before, guys out there with, technicians with, UL list of electrical tape wrapped around wrenches, stuff of that nature, all very dangerous. There's no, within that battery string, you come across that potential of even a 500 amp hour battery. That wrench could pack itself, and then it'll stay there until that battery discharges or heats up or explodes, or whatever that final end result is. So we strongly recommend 1000 volt factory insulated tools. We go out with a digital voltmeter. We mentioned the low resistance ohmmeter for straps. You had mentioned you're using the Biddle Byte, so that's an impedance meter. Flashlight, amp meter, and a temperature probe are pretty much what we go out into the field with when we're going to maintain a battery system in Rectifier. These are IEEE recommendations. Battery manufacturers pretty much adhere to this. So if you go through the manual, you'll see that they're recommending monthly routines if possible. Sometimes that's a luxury. Everyone's stretched thin for manpower or technician power availability, but check overall voltage, compare that against the charger output, looking again for any kind of drop. Ambient temperature, again, I'm not going to go through and read everything, but that's just a monthly is pretty much just a walkthrough, make sure flames aren't shooting out of the rectifier or out of the battery. So again, a visual is really what the monthly really turns out to be. It's not a bad idea. Like I said, the flow current is very important. If you can get somebody to once a month, definitely once a quarter, to put an amp clamp on the battery string and document that. And again, what we're looking for is a trend. It's
where would you put the amp clamp at?
The amp clamp can go it can go anywhere within the string. On the most positive and negative, obviously as a circuit,
I guess it doesn't matter. Huh?
It doesn't matter. Just clamp it. Usually, it's nice to grab it right at the positive. Usually, your installations, from what I could tell from the size of your batteries, I believe they're all single conductor. If you have two 500 MCMs landing on a large battery, obviously you clamp each of them because sometimes the jaws just aren't wide enough to get around both of them.
Right.
Or sometimes we say, if you can, grab an intercell connector within that string that the amp clamp will fit around, so you don't have to add them up. But just anywhere in that circuit is fine to grab that. And that's, like I said, I've really impressed that on your people as a very useful tool in heading off or getting ahead of any potential problem. Quarterlies are
I could tell you right here.
Yeah.
What they do monthly, they do these visual inspections monthly. I'm going to pull this up just to see. But you can go on while I do this.
No. Go ahead. That's fine. I check out.
I think they check voltages for each cell. Let's see what else to do. It's taking a while. Okay. Yeah, let's see. Yeah, it looks like just a visual check plus the voltages per cell check.
Voltage. Again, I know it's easy to add it to it, but if you're doing that on a monthly, that's fine.
I do the battery charger amp reading just on the gauge there.
Okay, and actually that's fine. Looking for a difference in that, the issue there sometimes though is if you've had an added load, it's like, okay, well, hey, it's reading, and also depending on the rectifier, whether or not it's analog or digital, on a battery, we're looking for like a 2 amp difference is a pretty significant change in current. Mm-hmm. And that won't necessarily be captured on that rectifier because again, your load could be changing depending on what's running when they go to check that, and the tolerance is not that tight. So
you could add on to the check sheet and say like, do you have any loads on at that time? What are those? I would really recommend
clamping somewhere at the battery, the cable going in or out of the battery, positive or negative, or somewhere within the battery. I would recommend, or at least if they don't do that monthly, quarterly, absolutely. That's really, they may not be looking at that at all. I'll be honest, a lot of people within the routines don't realize how useful that information is, because that current, again, typically it's 10 milliamps per 100 amp hours, so you're looking less than an amp. So if I go in on a 500 amp hour battery and I see an amp, and it's like, okay, that's, it's a little high, but that's okay. That's not, but I go in and I see 3 amps. That's a big, now that's got my attention. So it's not a big, it's a 2 amp difference is really grabs my attention on a battery. And then also if we're trending it, if we're saying, hey, this battery 2 months ago was an amp or less, and today it's 3 amps, and I know it, it didn't just come off of the discharge, you're not getting a recharge, I know I want to take a further investigation of that battery. So yeah, I would, like I said, quarterly maybe, if they could do that, I would absolutely recommend that they clamp that somewhere within that string or reading into that string, and not just depend on the rectifier. Quarterly, I don't know what they're doing. How often do they do the bite testing? Are they doing that quarterly or yearly, or do you know
they do the bites a year? Every year. And off of that, I can show you here, right here. Yeah, they do use the bite 3 every year for all the batteries. I'm going by IEEE, they would say quarterly, but again, it's easy to spend technician dollars and time doing. And I agree with you. And that's something I'm going to basically, the point of this is not only for my knowledge, but also to see where we're lacking and where we can improve. So that would be something we could look into.
I'll tell you what, more than anything else, I would say also having somebody. I was at a site in downtown Manhattan, a major communication site, central office. Mm-hmm. They had 5 strings of batteries. They were doing internal readings on them. They were documenting them, and they were. And this was actually just a voltage log, which again I don't put a lot of value in, but a technician would come in quarterly, do the voltages on all the individual cells, log them in the book, and then put the book to the side. We're contracted to come in and load test those batteries after a couple years in service. We go in, we look at the log book. And there's no lie, one of the batteries, the battery disconnect was open. So, and we looked at the log book. All the other, the 4 strings, everything is like 2.25. The open string is 2.21. And then you look further down, it's 1 point. You could actually watch that battery self-discharge with the log. But no, the reason for that story is it's really more important to have somebody at least reviewing that data also. Are they looking at the trending of them? So even if you're doing yearly, which is, like I said, IEEE would want it more frequently, but even yearly. But is somebody really looking at, hey, what was that previous year's number, and what was the year before that? So are they trending it? Is anybody really looking at that?
That's what we just started looking at. Actually, we have another, like a third party helping us out with trending these values, and they put out a report. I think I sent it to you, where they trended the cell impedance and the cell voltages.
Yeah,
that was the only thing they trended.
Yeah, they were a little more wrapped up in the voltage than what I thought. I thought they spent probably too much time in that report on voltages. Again, it's handy, but it doesn't. Like I said, impedance or ohmic value, current, and temperature. Again, if those would be the three things I could only look at, that's what I would want to look at. But like I said, I wouldn't get too wrapped up or spend too much time in the voltage aspect of it. But that being said, also, like I said, trending, pardon me, is really different, is really important. And again, we're looking for that 23%. And then what do you do with that once you do hit that threshold? Well, okay, what's the age of the battery? So do I expect to see a 30% change or deviation in ohmic readings after 7 years, 8 years? Yeah, okay, then you can start to budget. But like I said, you have to look at the whole picture. And like I said, more often than not, we use those values as triggers for capacity testing or load testing. So that's because again, those meters and those companies hate when you call them meters because hey, these are test sets. So those testers are okay. They're certainly better than not doing anything, but they give you an idea of what's going on. It's certainly, I would never hang my hat and recommend a battery replacement or bless a battery for performance based strictly on those readings. And then yearly inspection of the battery should include everything that we talked about before. And then also looking at AC ripple, current, and voltage on the battery. A lot of times that'll be an indicator when the capacitors need to be changed on the rectifier. And there's a rectifier section we'll touch on here too. And then also the cell-to-cell terminal connection resistance that we talked about before. And,
is that something that? Yeah, the ripple current, is that just when you're charging the battery, or is that just when it's sitting there floating and something goes wrong with the capacitor?
Well, floating. Yeah, that's regular float service.
Okay.
Yeah, you want to check for.
So you don't get that
ripple.
perfect square, or DC wave, DC waveform, and then I see what you're saying.
Yeah, no, actually, in some of if you look at a battery schematically, it's a capacitor, and some real cheap and dirty utility chargers, you don't see it too much anymore, but they actually use the battery as filtration for the output. And the issue with that is the battery actually sees those as very shallow but very frequent discharge cycles, and that can really beat up a battery. But again, that's not an issue really related to the equipment that you have installed, but it is something that IEEE recommends to be monitored yearly. And then let's see, a second, what did I do here? Let's see. And again, these are IEEE. So then the important thing is, okay, well, now I'm doing all these readings. What, according to IEEE, requires immediate attention? So again, to kind of prioritize what's a real red flag and what I need to worry about. Connection resistance, more than 20%. So they're saying, hey, this is something that if you see a change in those resistance readings, that's something that's going to require immediate attention. Ohmic values deviate significant. Now they get to be they have to be somewhat vague in their description of what a significant deviant value is. We use 20% from the installation or baseline as a warning and 30% as an alert. And again, that's not saying it's time to change the battery. That says, hey, it's time for further investigation.
So you could have something that was. It's funny you mentioned from installation. So if you're trending it, that's the best way to do it. You could have a difference from the last year of 5%, and you could say, well, it's good, But if you look back, it's really 20% from installation.
Right, exactly. Yeah, you'll see a 2 to 3% drop off pretty regular. Right, and then but you got to take the long. You got to take the long view on that. You remember I showed you the battery when I showed the valve regulated and the loose cell from the front.
Mm-hmm.
This is the back of a battery that was installed in. This is also a central office application. I'm not sure what it is about telecom, but we seem to find quite a few issues with those. These very large cells, what they do, they remove them from the steel trays, assemble the steel trays, and then reload the cells. And just because of the weight, particularly you get pretty high up in these stacks, and some of these assembled trays with 3 cells in them each are, 1,000 pounds. What we think had happened here, they probably unloaded the cell and dropped it and assembled it, somehow cracked it, or it could have been from manufacturer, but probably unlikely. Something happened during installation. And then there was a ground fault. There was a crack. There was a path to current. So we threw, with an ohmic value, we could see the cell was heating up, drying out. Now, because of the steel tray, there was no real indication of temperature. It was probably warm about the back of this and would have been picked up on infrared thermography. But this rack was up against a wall, so we had no way of actually detecting that. So with ohmics and flow current of the battery, we're like, hey, we found, there's a suspect cell here. Further investigation pulled it out, and again, that's something you would never see looking at the front of that battery. It looked perfectly fine. Not a single indication that there was a potential issue with the battery. But again, that's wow. That's where those conductance and impedance readings come in handy. So again, any electrolyte found, any kind of leaking cell is certainly cause for concern, further investigation, cleaning. Flow voltage, and then outside it's so you come in there, you find, hey, this thing's in equalization, whatever. Obviously that's or undercharge. Hey, this is open circuit or well below voltage. That's something else that's going to require immediate investigation. Capacity testing. This is it's by and far the best way to determine the health and what that battery is going to do for your load when called upon. The IEEE recommends performance testing on valve-regulated batteries because they're so unpredictable as to their, and this actually goes back to their earliest generations of these batteries, very unpredictable. That's for various reasons, quality control, the way plates were formed back then, the way the batteries were assembled, they were very unpredictable in their the way they were going to act out in the field. The batteries that are being deployed, this last generation of batteries, and I'm talking batteries manufactured within the past 5 years, far, far more reliable and more predictable than what was, originally deployed. But because of those initial batteries and all the issues surrounding them, and it was a nightmare when they were first released, the valve-regulated batteries back in the 80s. IEEE said, hey, you really got to test these things every 2 years. Recommendation. Again, this is not fun. That's the recommendation. But it's, load testing is an expensive process. It jeopardizes your, depending on the quality of the people doing the work, it jeopardizes your system, your load. You really have to know what you're doing. My personal recommendation on valve-regulated battery is probably after 5 years of installation. Do an acceptance testing if you can when installed, but then after that, 5 years after being in service, and then I would base it on conductance readings, and then then maybe you go to every 2 to 3 year period of load testing. No one can afford to do every 2 years. But again, it's a recommendation, and that's what we.
Well, so you got a picture here of it. I was going to ask what it looks like.
Well, I was going to say, these are some of the. These are Why I didn't put this on vibrate, I don't know. This is just to show some of the system. We use Canon load banks, but depending on the amp hour, the size of the battery, we have larger units that roll in. And then even this little guy here, I think he's rated at 400 amp hour. It's pretty amazing how compact some of the newer stuff is. And this is the master, but there's slave units you can parallel to it, and they pardon me, and then we're again load testing a 48 volt system here. We have automatic data acquisition for larger cells. This happens to be a NiCad, but again, when you're looking at 60 or 120 cells, the load test is typically designed around the application. So a switchgear battery is usually designed for high rate short discharge. So usually their batteries of that nature are load tested at the anywhere from the 15 to 60 minute rate. So the manufacturer publishes the rate, hey, this battery can supply this much constant current for this period of time to this specific end voltage. And then, we monitor the individual cells. Is that because
the loads on that are so quickly, such quick loads, like breaker closing and that kind of stuff?
Yeah, exactly. So you want to typically test that battery at a high rate because you're not only looking at battery capacity, you're looking at connection performance, you're looking at the whole thing. So you want to do a very short, you want to try to mimic the load as much as possible. Conversely, emergency lighting battery, a telecommunication battery, or another battery that's designed for, hey, this thing's sized to run 8 hours. Well, you're not going to run an 8-hour load test, but the industry standard on that size battery is typically 3 hours. So long duration battery application, 3-hour load test, short duration battery, anywhere from 15 to 60 minutes. So because those, what's that?
Well, I was going to say, what loads you use, I mean, do they actually bring out a resistor bank, or do you just use, depending on the application, the actual load you're trying to test?
No, we bring out we bring out a resistive load bank. We never want to jeopardize because we are taking that battery to a terminal end voltage that may be very close to where the equipment cuts out, depending on what you're supporting. We come in with a temporary battery, and hang on, I think I have the. Actually, I think there's a slide here. Okay, no, I don't have it. Well, actually, I do. I reference it here. Depending on the application, it may require a temporary battery equal to the battery being tested. We utilize infrared thermography at the time of the discharge and recharge. And then also, we don't want to slam a discharge battery right back onto the system, because now you have a discharge battery. You land that cable, you'll draw an arc, the rectifier will go in the current limit. If there's a parallel battery, you're going to have a ton of inrush current from that battery, supplying the discharge battery. So we bring in the temporary rectifier and recharge the battery to, within close to the plant voltage, and then reattach that battery to the system so as not to cause a shock to this. So it's an involved process. It's not and it's not it costs money. You have to have very qualified people doing it, and that's why, like I said, when you see something like a 2-year routine recommended by IEEE, that's just not going to fly. So, but no, we do recommend not using the equipment, because the other thing is, well, they say, well, what we'll do is we'll just run it for an hour or whatever. We'll try to get an idea of what it'll do, but we won't get to our terminal voltage. And if we get close to it, we'll just turn everything back on. Again, you want to run that battery all the way out to an end, to the designed end, so you can see that curve and that, because the battery could look initially out of the gate doing well, but it could quickly, for lack of a better term, run out of gas. You get halfway through the test, and you can see that sometimes. Some batteries, depending on the failure mode, they'll look really strong, and then halfway through they'll just dive. And you won't get that with just a snapshot of the front end of the load of the battery. So again, it's not a bad idea if somebody wants to do that. At least get it, but keep in mind, if it's a single string application and you have a weak or a bad cell and a cell opens up It's a chained weakest link theory. That thing opens up, you'll drop your load. You won't have time to respond. Anyway, there's a few things why we recommend an actual full
That's
load test.
something you talk about, bringing a temporary battery out there. So if they don't want to cut service off, they want to make sure they have something. You bring out a temporary battery to replicate, and then you do your test, and then several hours after recharge, then you can put it back in service.
It's usually a 2-day process. We go in, temporary battery installed parallel to everything while everything's hot.
Mm-hmm.
Then that battery's isolated. That's if it's a single string application. Sometimes applications are multiple strings, and then they'll say, okay, we can afford to lose a little bit of that capacity. You take that guy off, test him, recharge him, bring it back on, and then do it that way. But if it's a single string installation, or they don't want to take the chance of losing any capacity, we bring in a temp parallel in charge. And I'll honestly, sometimes we'll come in, the battery will fail miserably. They're like, okay, leave that temporary battery on, and then then we'll work around the replacement or whatever needs to be done on the service side of it. So, yeah, that is not totally uncommon for us to leave our temporary battery, because we've identified because usually when you're load testing, there's something suspect. So usually incorporated with the capacity test. And I did it again. Let me see here. Okay. I don't want to get too much into this, but just to let you know, there is remediation or a service for batteries that are exhibiting signs of dry out. And that's more often than not the failure mode of valve regulated batteries. It's just a function. I mentioned the one-way relief valve. They're not designed to have water reintroduced to them or any other work done to them, but we've pioneered a process by which we actually can rejuvenate and recover capacity in valve regulated batteries. So in its most basic form, we introduce deionized water back into the battery. We do equalize the battery at that time, at the end of it, and then we install a retrofit catalyst. I'd mentioned before, catalysts, well, by definition, they're not actually used in the recombination process. They just facilitate the recombination of the hydrogen and oxygen in the headspace of the cell. And it's done by what that, in between the picture there, that's the pressure relief valve, is this top portion of the battery. This cage encapsulates the catalyst itself. So the hydrogen and oxygen are recombined here instead of the negative. And that helps recharge or get the negative plates properly polarized. So it's just something I wanted to touch on, to say that it's not necessarily a done deal. Most people have to just replace a battery when exhibit signs dry out, but there is actually recovery for it. And it's a proprietary methodology pioneered by Battery Research and Testing. And this just shows some batteries we've trended ohmic values, and that's what this is. This is actually Mohs. So this is so we saw a pretty significant rapid drop off, performed the RWR recovery, and then we monitoring. We did a load test before and after, and then now we're still trending the battery, so you can see how that flows. And the process itself is actually now recognized by IEEE. So in their addendum to the maintenance, why they don't actually say the process, because it is a trademark process by us. The three key components, the catalyst, the rehydration, and the high rate charging, are all referenced. So that's how they kind of got around at least recognizing it without actually saying, hey, we recognize IOVR. Now there's some things that all the water and catalysts in the world are not going to get you around. This is what we do. We open up that valve to each of the cells, and we inspect them with the borescope. These are negative straps. This one here is a healthy one on the left-hand side. this is one that is exhibiting excessive corrosion. So, right off the bat, we would say, no, this battery's not a candidate. There's no hope for this battery other than replacement. So that's why our success rate with that particular process is so high, because we weed out, the good and bad candidates for it. So we have about a 98% success rate on recovery of batteries. That's not to say that we do 98% of the ones that we come across. It's just saying, hey, we're very confident in the ones that we take on for that process as far as recovery. Okay, so rectifiers. Rectifiers this is input. I don't really have IEEE information related to that. This is based on Hindle. I don't know, and LaMarche, their recommended maintenance and troubleshooting. I think do you typically have LaMarche rectifiers deployed in your network, or?
Yeah, these are, I would say, about 90% LaMarche from the places I've been. Yeah.
Okay, so they're solid rectifier. They're a very, very, very good brand, good support. Again, we're not a manufacturer's rep for anyone, for a battery or rectifier or distribution. So we're independent. So I don't have an axe to grind for anybody. So that's why I give you an honest opinion. Like, hey, LaMarche, good charger. I can tell you GMD battery, not so great. East Penn battery, very good. Hindle chargers, very good. Some of the older Benning chargers, not so good. So we'll give you an unabashed opinion on particular equipment that you may have out there. But this particular maintenance routine is I think is primarily Hindle. But again, they're the same for the rectifiers across the board. There's not a lot you can do for predictive or proactive maintenance on rectifiers other than we'd mentioned the DC capacitors. So when you guys are out there maintaining the system, electrical connections, again, you're looking for the quality of the AC input and the quality of the DC output. You're looking for ripple voltage. Thresholds, I don't know if they're checking the alarm set points. Usually they're set up from install and they don't deviate from there, but you either have a high voltage alarm, a low voltage alarm, and those are usually indications or set points for the DC output of the rectifier. They can be checked and verified, but again, they're not usually done as part of a routine. They're usually done.
Well, we saw
install.
We saw a couple of those negative ground alarms on the ungrounded systems.
I touched base on that because we have seen, because I know that we had that, have had that issue. This is the capacitor replacement is usually on a 10-year interval is what they recommend for capacity. Rectifier ground fault alarm, because I know that we've touched base on this situation in the past. I wanted to make sure that I incorporated it into this presentation. 3 places where those alarms can be caused: load somewhere in the battery or the cables, or internal to the rectifier itself. It's not uncommon or unheard of to actually have the alarm either a faulty card or someplace within the rectifier itself. Again, to troubleshoot or isolate the alarm is a little difficult when in service. We recommend identify which one of those 3 places where the alarm's coming from. People are usually quick to look at the battery, and that's not without cause, because a battery, a ground fault alarm within a battery can happen depending on how that battery is maintained. So sloppy housekeeping, when they're rewatering, again, this really goes back more to the flooded batteries, but where technicians are periodically reintroducing water into the electrolyte, bad housekeeping, they'll have water, sometimes they'll have a spill or something around the battery, or they're also prone to post-seal or jar cover leaks, and acid by nature will creep and get to the rack at some point and it'll cause cause a ground fault indication at the battery. So that's why people usually look at the battery right away. But the thing is that if you can, isolate the battery, take that totally out of service. Don't just open the disconnect, but remove the cables. See if the alarm goes away at that point. If the alarm's still present, then if you have the luxury or at some time of a scheduled outage or what have you, remove the load from the rectifier and identify it that way. See if the problem follows the goes away with the items as you're removing them. If you remove the load and your alarm's still present and your battery's not connected and the alarm's still present, well then it's within the rectifier. Mm-hmm. And then we had also talked about if the alarm is detected at the battery, we recommend using a voltmeter and then checking the battery most positive and most negative to a ground source. Typically the racks are grounded, or that steel tray that the battery is installed in is grounded. We remove the inner cell from, say, jar 30 to 31 or 29 to 30, somewhere in between. And we kind of break the battery in half and try to isolate. We're looking for voltage potential from that half the battery to the tray, and then just keep shortening it down to, just trying to track it down. Ground faults are not fun. They can be very, a friend of mine is he works a lot with solar arrays and the charging systems and batteries around them. And apparently it is a very prevalent problem with renewable systems. And he just rips his hair out. We kind of talk batteries and complain to each other about certain things. And that is a very prevalent problem in their industry for whatever reason. So, but yeah, we'd be more than happy to talk to a technician if they want to lean on us, or actually as they're out in the field. We had a job ticket actually open on one of the issues when we first started talking about a ground fault issue, the active one that you had, and I had reached out to LaMarche and they opened a ticket number. They're actually very good for technical support. So also we can also put you in direct contact with them. We have some inside service people that we deal with that we have their direct line, and they're very good, very, very good people.
Is that
to work with over
for
LaMarche?
I know you guys come out.
Ohio.
Yeah, I know you guys come out and do battery maintenance for several customers, but as far as chargers and UPSs go, you guys would go to LaMarche?
We do charge. No, we do chargers as well. We do particular. Okay. The thing is, we don't carry just because the amount of different chargers out there. We don't necessarily are carrying or inventorying control cards or alarm cards or all the items. So we can go out and troubleshoot, and then usually we end up ordering parts in. We don't, like I said, inventory a ton of them. We do inventory capacitors for most of the manufacturers, but again, there's a lot of different sizes and a lot of different. So UPS systems we do not do, and UPS is that specific of an item that we, like I said, and likewise we work with the inverters, Bories. There's a few other, AEG, Schneider, APC, Schneider APC Electric. So we work with them, and we work with some of the largest dealers in the United States, but we do not. That's just a whole different animal, and that's where you have to have a very specific technician. Now, we'll do the battery support for them. We'll partner with them because a lot of times they don't want anything to do with the high voltage and potential of the battery. So we'll come in and do that aspect. But no, we do service and maintain all major rectifier manufacturers. So.
Okay. Well, yeah, we were getting a low DC current alarm on a couple of these chargers. I wasn't sure if that was a major thing or not.
Again, that would be usually, yeah. An LCA or a low current alarm is usually at the rectifier is at 0. LCA, and where I've come across that have usually been parallel rectifiers. I don't know if you have single rectifier installations or parallel, where the load is so small. Typically, they try to load share. rectifier systems by design are usually like an N+1. So you have a certain amount of redundancy within the system that you can lose a rectifier and not drop your load or have to run on battery. So more often than not, the loads are usually so low that they'll have two rectifiers and they won't load share. Load sharing can be difficult, and that's where you get an LCA alarm. The one rectifier just kind of takes over and carries the complete load, and that's why you see that alarm. Other than that, that's usually see a LCA along with an RFA, which is a rectifier fail alarm, and that just means, hey, the rectifier is offline, either the breaker tripped or AC power was lost to it or something of that nature. But yeah, I would investigate that LCA alarm. The only other thing I would say is that maybe that threshold's set too high. Usually it's set for like just at 0 or just slightly above 0 amps. So I would investigate that a little further. And again,
because we don't have parallel. I think we're all single chargers.
All single
circuits.
Okay. Yeah. Okay. And then an LCA alarm is very unusual without a rectifier fail. So I would.
Well, yeah, because you got to have something, right? You're charging them. I mean, you're connected to the battery, right? So like.
Yeah. Well, though again, sometimes the battery, like I said, a properly operating battery is throwing less than an amp, and that might not be enough for that rectifier to, like I said, depending on that threshold. If that alarm is not set at 0, if it's set at an amp or 2, it still may may not realize that it actually is supporting something as low as a load of a battery. Okay, if you think of how small half an amp is. Did you say you actually have a couple of that are exhibiting a low current alarm?
4. I noticed 4 of them when I was out there, and a couple of them were probably for the Navade lights. Okay, so we got 3 of them at 24 volts, and I think a couple of those are those battery, like car batteries, and then the rest of them were, I think, the VRLAs.
It very well might be that it's just is it backup for the Navilights, or does it drive the Navilights all the time?
I believe it's backup. Yeah.
So that might be an accurate indication. The current is so low charging the batteries, and if that rectifier is not supporting those lights, and unless usually the rectifier is supporting those lights when they're on. I'd have to take a look at that. I'd have to take a further. And the amp meter itself, did that appear to be reading 0?
I don't think they have an amp meter on the front of those.
Oh, yeah.
I don't remember seeing one on the front of that. I know they have a voltage, but I don't remember seeing an amp.
They may
the
not.
one on the Navade's fairly small.
Yeah, that's what I was thinking. Well, then that's when you mentioned about the car style, the monoblock batteries. That's usually a very, those batteries are usually used in very low load applications. So, yeah, I'd say what I'd recommend if you could, if you have a technician available or somebody out there that could clamp that I would verify that with, hey, could you clamp on the output of that just to see what's going on?
Right. Yeah, I think two of these are the, like one's a 125 volt. That one I'm a little concerned about. And that one's for the generators. But anyway, so I did notice that. And then I also noticed a couple of our chargers are really loud, which I'm fairly certain is just the transformer inside of there.
That's exactly what it is. It's the LAT or whatever they call and that's usually an indication of an older, at that point, transformer replacement is usually rectifier replacement, unless you're talking a very large, system. But if it's it's
going to cost more, you might as well just replace the whole charger.
Absolutely. If you're talking a 50 amp charger or smaller, that's usually, and again, depends on the age of it and warranty. And there's a lot of times too, manufacturers will warranty the transformer. They may give a 10-year warranty or 15-year warranty on the transformer just because they are so robust. They typically don't go bad. So that's something you may want to look at.
Lamarche, yeah.
Yeah, look at the age of the unit, and yeah, it's not uncommon just to have them just rattle very very loud. And the other thing too, sometimes that I'm not sure if harmonics is the right word, but it seems like the less the load, sometimes the louder they are. If they're just sitting there not doing anything, they rattle and they hum like heck, and then you get them under load, and then that dissipates. So. But yeah, I would check on the age of it as well. But yeah, I would think probably replacement or budgeting for replacement is probably the next step on them if they're 15 years whatever or older. I don't know how old even how old that particular platform.
How facility was 2000, so it's almost 20 years, and
yeah.
I believe most of those are probably an original.
Isn't that funny? You said 2000. I'm like, oh, it's not that old. And then you said 20 years.
You're right.
That's funny. Yeah. So, like I said, service life of a rectifier can really be where I can easily ballpark different battery manufacturers. Rectifiers are all over the place. I mean, we've seen 25-year-old, 35-year-old. Chargers out there, again, with the maintenance of the caps, obviously have been changed over that lifetime, but they're out there plugging away. I mean, they can really vary widely in their service.
Any remarks on ferroresonant transformers inside of these guys? I noticed that they had them. Well, like I saw them on the UPSs, I know that, but apparently those things always operate in saturation, and there's a higher risk of those catching fire than regular transformers. And I just I've heard that you don't necessarily need them if you have solid state filtering
I was
and all
going to
that.
say,
but
some of the industrial rectifiers now they've referred to the solid state or switch mode rectifiers. I know utilities in the United States have actually been slow to migrate to them just because, again, there's just an embedded history of the ferroresonant style rectifiers. But again, like everything else, they've now proven to be very robust. Their footprint is so much small. Their power density is just, you have a 300-pound rectifier, and now you're changing it with this 45-pound or 40-pound rectifier that's operating much more efficiently, and you don't have, some of them now are even modular, where you can have a shelf, and we're always about redundancy. So if you have a 25 amp load, you mentioned a lot of your installations are single rectifier, we really, whenever possible, we try to design in a certain amount of redundancy. So we would go with two switch mode rectifiers. They're so much cheaper. They're so much smaller. And now you have the redundancy that you can take one out of service for maintenance, or if it just needs to be replaced and not have to worry about a temporary battery. Likewise, again, footprint gets to be an issue and stuff like that. But if a plant is calling, or an application is calling for a 600 ampere hour reserve, we'll recommend 300 ampere hour, or usually a little bit, bump it up a little bit higher, 350, whatever, parallel systems, so that, hey, one can be taken out of service without having to bring in a temp. You don't always have that luxury. So now you can take one off. Now you can take one off and do some troubleshooting. But again, there's additional cost, right? Usually there's a little more infrastructure. There's more cable, there's more. But, like I said, that's just kind of our philosophy when possible. Again, you don't always have that luxury, but we highly recommend that when people can design that into new systems or replacement systems to go with some kind of redundancy.
Right. Well, one of my, I tried to write a couple of questions on here, but I think you answered the one about recommendations for capacity testing. I think you covered that, and that was good to know. And, it seems a little complex, right, if you've never done it. potentially having you guys come out for the first time and kind of showing our guys how to do it, so that they're aware of it. And I'd like to know too. I'm sure you guys do this for your customers at a certain frequency,
We do. No, we're load testing is probably 20% of our business. We get contracted even by other maintenance companies. Like I said, they'll come in and they'll have something suspect and they'll want something qualified. Or like I said, it's actually getting to be more of a common practice for commissioning or acceptance testing of a new installation. And when we come in and capacity test a battery, like I said, like a new installation, we'll also utilize the load banks on the rectifiers and put the rectifiers in the current limit and make sure that they're, and again, we utilize them for thermography. So we're going to shoot everything from the breaker that, again, looking for. A lot of these are never going to really see load unless it's like you've been on battery for whatever reason. Now you have a discharged battery and you're going to recharge that rectifier is going to current limit. And if you have a problem with either the breaker feeding that rectifier or the rectifier itself, and that trips off, now you have a dead battery and a dead rectifier. So, like I said, it's, there's a that's getting to be a little more popular, some of the full system commissioning testing. But when it comes to battery testing, we're very transparent. We're happy to show anybody how it's done. We provide a detailed method of procedure, step by step, and then there's a backup plan if there's if there is an issue or something's identified, and how. So it's pretty detailed. Again, it's something we do for power generation, nuclear power plants. We work in several of the Exelon facilities. We do a lot of work in the communication space, and certainly done a lot in the chemical industry as well. So yeah, it's again, nothing really, not a lot of. It is interesting, like I said. I still find it interesting. I've been doing this now almost 30 years, and I still find this stuff intriguing. And it's always interesting about the data that you get. There's always I think I've seen everything, and yet something will still surprise me every so often. So
I believe it. Well, now you said that this was recorded, so this would be good to get a copy of. But you also mentioned in the beginning another slide or a presentation that could be useful.
I do. I have one. Yeah, like I said, if you want that, I'll send you this, and I'll send you that one separately. That's and that's actually been put together. The one I have was put together by Philadelphia Scientific. They're the ones that manufacture the catalyst for most of the major OEMs, and then they supply us as an aftermarket item. So yeah, that's I'll send you that. But if you see Philadelphia Scientific on it, that's why it's not mine. Okay. Depending on my audience, I'll pick and choose slides from it, but I'll send you the complete presentation so you can look at that.
Well, this was great. I really appreciate you taking the time and doing this, because it was pretty helpful. And like I said, I'll send the copy of this to our guys at Hoover as well as Mobile Bay as well.
Okay. Well, again, I appreciate your time. I think the way this recording will come up as a link, I need to double check on that whole thing. So, matter of fact, it probably should be. Let me turn off the recording now. Let me see.